Okay, what we want to do is we want to look at Taylor and Maclaurin polynomials, and we're going to be focusing our attention on the Maclaurin piece of it, which is really a specialized Taylor polynomial, but we want to get some understanding and insight into where they come from and why they work. So let's just go ahead and get started here. If I want a polynomial that approximates e to the x, then one of the first conditions that I would like to be true is that my polynomial better have the same function value as e to the x. E to the 0 is 1. Now the easiest way to get that to happen is to just let my polynomial equal our constant function 1. And graphically what that looks like is a horizontal line through 1, that it does a really good job right here at 1, but it does a horrible job everywhere else. I mean, if I tried to plug this value in right here, maybe this is 3. 3 gets mapped to 1 here, but 3 really goes to e cubed way up here, okay, not even anywhere close to 1. So this, while it does approximate it really good at 1, it does a horrible job everywhere else. So how can I get a little bit more accurate? Well, what if their slopes were the same at 0? In other words, what if p prime of 0 equals f prime of 0? Okay, you can go back to the graph now and see, or kind of imagine what that is. Remember, we want the function value to be the same at 0, but now we want the slope to be the same. Okay, and if the slopes are the same, that's what it would look like. I mean, it's a tangent line. And you can see that this is a little bit better approximation. You can see if we go back to, well, clearly, 0 gets mapped to the same number, but now if we approximate maybe out here a little bit, you can see that the blue and the yellow line are, and most likely what's going to occur is the closer you get to 0, the better the approximation that it's going to be. What is f prime? E to the 0 is 1. So what does this look like? What does this polynomial look like? Well, we're going to keep our original term of 1, but I'm not going to write 1. I'm going to write f of 0 instead. I want to keep it general. And we're going to add to it f prime of 0 times x. Now remember, f prime of 0 is just 1 as well. So we really have 1 plus x is really what our function is. Now, why did I add that? Well, it doesn't start to make sense until you start taking derivatives of this thing. Let's look at the first derivative of p. And the first derivative of p, f of 0 is just a constant, so that's just 0. And the derivative of f prime of 0x is just going to be f prime of 0, which is just 1, remember. So if I evaluated p prime of x at 0, there's nowhere to plug 0 in over here, so it would just be this constant. So this condition is met. I can also go back to my original polynomial right here, and I could plug 0 into here. If I plug 0 into here, this term goes away because f prime of 0 times 0 is 0, and I'm left with f of 0 preserving this condition. Okay, well, what if I wanted to make this more accurate? What if instead of saying, okay, the function values are the same, the slopes are the same at 0, how about their concavity? What if they had the same concavity at 0? I don't know if this is exactly what the function would look like, but you can get an idea that the more terms I'm adding to my polynomial, the more close my curve is going to look like the blue curve. Okay, so you can see that they have the same function value at 0, they have the same slopes, and now they have the same concavity. In other words, their second derivatives are the same. Okay, I'm trying, and my new polynomial, not only do I want the second derivatives the same, but I want these other conditions, this guy and this guy, I want to preserve those as well. So how do we do that? Well, I'm going to keep my first two terms, which are f of 0, which is just 1, plus f prime of 0, x. Now let's add to it 1 half x, well, not x, f double prime of 0, x squared. Okay, now why the 1 half? Well, like before, what we add doesn't necessarily make sense until we start taking derivatives and see what happens when we start taking derivatives of this thing. So if I look at the first derivative of my new polynomial, this is my new polynomial, and I look at the first derivative of it, look what happens. The derivative of f of 0 is 0. The derivative of f prime of x is just f prime of 0. And the derivative of this last term here, when we use power rule, is just going to be f double prime of 0 times x. That 1/2 kind of vanished. Now let's look at the second derivative. And the second derivative is going to be, well, this is a constant, so it's 0. And the derivative of this will just be f double prime of 0, which is just 1, because remember the derivative, any derivative of e to the x is e to the x. And when I evaluate p double prime at 0, I get back f double prime of 0, satisfying this condition here. Okay, now you can work your way backwards. You can go to your first derivative, plug 0 in for x, and see that this condition is met. You can go back to this original polynomial, plug 0 in everywhere you see an x, and this condition is still maintained. So we're maintaining all of our conditions while at the same time adding things to our polynomial to make it look more and more like the blue function up here. Okay, well, as soon as we leave the second derivative, it becomes a little bit harder to visualize on the graph. So, what would it mean for the third derivatives to be the same? Let's use light blue. What would it mean for the third derivatives to be the same? And conceptually, I mean, I know what it means, but conceptually, I can't really draw it. I don't know. It goes beyond my ability to understand that. But it really means, what if the concavity's rate of change was the same? What does that mean visually? I really don't know. So let's just do the math over here. Well, let's take, like the previous cases, let's take the original function that we had to work with, which was f of 0 plus f prime, that's a plus, it's a bad plus, plus f prime of 0 x plus f double prime of 0 times 1/2 x squared. I know I wrote it in a different order. Sorry about that. Hope that doesn't mess you up. Now what's the third term going to be? Well, if I did 1/2, well, I'm going to run out of room. I can see that already. So let's continue it down here. This is my third. This is my cubic term here. I'm going to do 1/2 times 1/3 times f triple prime of 0 x cubed. Okay, so this right here is my new polynomial. I've added another term to it, and let's do this very quickly. Let's see if I can do this quickly. If I look at the first derivative, I'm going to get f prime of 0 plus f double prime of 0x plus, let's see, now I'm looking at this term right here, and if I bring the 3 out front, it reduces with that 1/3, and I'm left with 1/2 f triple prime of 0 x squared. And very quickly, the second derivative is equal to, this is going to be 0, this will be f double prime, and then this term right here is going to be f triple prime of 0 x, and then last but not least, the third derivative of p is just going to be f triple prime of, not 0, or yeah, 0. Okay, so again, just like before, you can go back and substitute 0 in for x into the third derivative to make sure this condition is met. 0 into the second derivative to make sure this condition is met, 0 into the first derivative to find out that this condition is still met, and 0 into this guy right here to find out that this condition is still met. Okay, so if you start to look at what's going on here, you'll start to see a pattern emerging, and you'll see that we have an f of 0, an f prime of 0, f double prime, f triple prime. Okay, you'll also notice that there's really an x to the 0 here. This is really an x to the 1, x squared, x cubed. So one thing for sure is if I wanted to add a fourth term to this, one thing for sure that I know is that there's probably going to be the fourth derivative of 0 multiplied by x to the fourth. But what are the numbers in front of f to the fourth? Well, let's look up here. There's really a this is going to get kind of messy here. There's really a 1 over 1 there. There's really a 1 over 1 there. So would you agree that this is going to be 1 times 1 half times 1/3 times 1/4, which is really a 1 over 4 factorial. This right here is really 3 factorial. This right here is really 2 factorial. And this guy in front of the f prime can be thought of as 1 factorial, and even in front of the f of 0, that's really 0 factorial, which is 1 as well. Okay, so what is the general rule for this then? For the Maclaurin polynomial, we have p of x equals your function, whatever function you're approximating. We used e to the x up here, but this could be for any function that you can take derivatives of. F of 0 plus f prime of 0, f prime of 0, x plus f double prime of 0 times 1 over 2 factorial x squared. We'll do one more here before we generalize it, plus f triple prime of 0 times 1 over 3 factorial x, I'm having trouble with my pen here, x cubed. And then finally, if we ran out to the nth term of this thing, plus dot dot dot, we could say f, the nth derivative of f, if it had an nth derivative. That's the assumption here, is that you can take the nth derivative of it, over 1 over n factorial times x to the n. Okay, so this guy right here is called the nth Maclaurin polynomial for f. And the more terms that you have, the better approximation you're going to have of your original function centered around 0. Now, with the Taylor polynomial, all a Taylor polynomial is instead of centering it around 0, you can maybe center it around some c value. Okay, and that's just adjusting this formula right here. It's not too difficult. We can talk about that in a later video. Hope that made sense. We'll see you around.